All right. Hello, everyone, and welcome to the third week of my public astronomy talks. Tonight we are going to be talking about not only the history of astronomy, but also the science of astronomy and what defines science in general. So tonight's quote is from none other than Maria Mitchell, an astronomer and the first woman elected to the American Academy of Arts and Sciences, an organization that is still around today. So her quote is, "We especially need imagination in science. It is not all mathematics nor all logic, but is somewhat beauty and poetry." So the rigorous methods of science, of modern science, have proved to be among the most valuable inventions in human history. These methods have enabled us to discover nearly everything we know about nature and the universe, and they also have made our modern technology possible. So tonight, we're going to explore the ancient roots of science, which grew out of experiences common to nearly all people and all cultures. So scientific thinking comes naturally to us. By about a year of age, a baby notices that objects fall to the ground when she drops them. So she lets go of a ball and it falls. She pushes a plate of food off of her high chair and, well, it falls as well. She continues to drop all kinds of objects and they all plummet to the earth. Through her powers of observation, the baby learns about the physical world, finding that things fall when they are unsupported. Eventually, she becomes so certain of this fact that, thankfully to her parents' delight, she no longer needs to test this continually. But one day, someone gives the baby a helium balloon. She releases it, and to her surprise, it rises to the ceiling. Her understanding of nature now must be revised. She now knows that the principle all things fall does not represent the whole truth, although it does serve her quite well in most circumstances. It'll be years before she learns enough about the atmosphere, the force of gravity, and the concept of density to understand why the balloon rises when most other objects fall. But for now, she is delighted to observe something new and unexpected. The baby's experience with falling objects and balloon actually exemplifies scientific thinking. In essence, science is a way of learning about nature through careful observation and trial and error experiments. Rather than thinking differently than other people, modern scientists, like myself, simply are trained to organize everyday thinking in a way that makes it easier for them to share their discoveries and use their collective wisdom. Just as learning to communicate through language, art, or music is a gradual process for a child, the development of science has been a gradual process for humanity. Science in its modern form requires painstaking attention to detail, relentless testing of each piece of information to ensure its reliability, and a willingness to give up old beliefs that are not consistent with observed facts about the physical world. So, for professional scientists, these demands are, of course, the hard work part of the job. At heart, professional scientists are like the baby with the balloon, just delighted by the unexpected and motivated by those rare moments when they, and all of us, learn something new about the universe. So, astronomy has been called the oldest of the sciences because its roots stretch the deepest into antiquity. Ancient civilizations do not always practice science in the same ways or for the same reasons that we do today. But they nonetheless had some amazing achievements. Understanding this ancient astronomy give us a greater appreciation of how and why science developed through time. So humans have been making careful observations of the sky for many thousands of years. Part of the reason for this interest in astronomy probably comes from just our inherent curiosity as humans. But ancient cultures also discovered that astronomy had practical benefits for timekeeping, keeping track of seasonal changes, and navigation. One amazing example comes from people of Central Africa. Although we do not know exactly when they developed the skill, some people in Central Africa learned to predict rainfall patterns from watching the moon. This kind of plot shows how it works. The orientation of the horns of the waxing crescent moon relative to the horizon varies over the course of the year, primarily because the angle at which the ecliptic intersects the horizon changes during the year. In tropical regions in which there are distinct rainy and dry seasons rather than the four seasons that we're more familiar with at temperate latitudes, the orientation of the crescent moon can be used to predict how much rainfall should be expected over coming days and weeks. The impact of astronomical observations is still with us in how we measure time today. The length of our day is the time it takes the sun to make one full circuit across the sky. The length of a month comes from the moon's cycle of phases, like we saw last week. And our year is based on the cycle of seasons. The 7 days of the week were named after the 7 planets of ancient times, which were the sun, the moon, and the 5 planets visible to the naked eye, Mercury, Venus, Mars, Jupiter, and Saturn. Note that the ancient definition of a planet applied to any object that appeared to wander among the fixed stars. That's why the sun and moon were considered planets, but the Earth wasn't. We obviously don't see the Earth itself move amongst the stars. So here you see a table I put together of those 7 traditional planets, as well as the French and Spanish names for them, as well as the French and Spanish words for those days of the week. You can see that, especially for the Romance languages, the days still can be easily traced back to what object they represent. So in French, Wednesday is mercredi, which is very similar to the word for Mercury, mercure. Vendredi is Friday, and it's very closely related to their word for Venus. When it comes to Spanish, Monday, lunes, very similar to La Luna. Saturday, Sabado, or for Saturno. For English, it's a bit more difficult. Obviously, we still have Sun's Day, Moon's Day, and Saturn's Day for Sunday, Monday, and Saturday. But the other days of the week come from the Germanic gods that represented those planets. So instead of Jupiter, we have a Thor's Day or a Thursday. That's where all the English names came from. Here is a question. There's obviously not a right answer to this question, but just something to think about. I'd be interested to hear your thoughts if you want to comment below or send me a direct message. Uranus is faintly visible to the naked eye, but it was not recognized as a planet in ancient times. So if Uranus had been brighter, would we now have 8 days in a week? Obviously, there's no correct answer to that. So think about it and let me know what you think. Now, I had planned to talk about ancient cultures before ancient Greece, like Stonehenge, the Nazca lines in Peru, Templo Mayor in Central America. But ironically enough, in order to save time, we won't be able to talk about how they measured time. So we'll move straight on to ancient Greek science. Because that's really where modern science can trace its roots. Ancient Greece rose as a power in the Middle East beginning around 800 BC and was well established by about 500 BC. Its geographical position, which you can see there in that map, placed it at a crossroads for travelers, merchants, and armies from Northern Africa, Asia, and Europe. And building on the diverse ideas brought forth by the meeting of those many cultures, ancient Greek philosophers soon began their efforts to move human understanding of nature from the mythological to the rational. Greek philosophers developed at least 3 major innovations that helped pave the way for modern science. First, they developed a tradition of trying to understand nature without relying on supernatural explanations, and they worked communally to debate and challenge each other's ideas. Second, the Greeks used mathematics to give precision to their ideas, which allowed them to explore the implication of new ideas in much greater depth than would have otherwise been possible. Third, while much of their philosophical activity consisted of subtle debates grounded only in thought, it was obviously not scientific in a modern sense. The Greeks also saw the power of reasoning from observations. They understood that an explanation could not be right if it disagreed with the observations. But perhaps the greatest contribution from Greece to science came from the way they synthesized all 3 innovations in creating models of nature, a practice that is central to modern science. Scientific models differ from what we generally call models. In our daily lives, we tend to think of models like model cars, model trains, that kind of thing. But a scientific model is a conceptual representation created to explain and predict observed phenomena. So, for example, a scientific model of Earth's climate uses logic and mathematics to represent what we know about how the climate works. Its purpose is to explain and predict climate changes, such as the changes that may occur with global warming. Just as the model airplane does not faithfully represent every aspect of a real airplane, a scientific model may not fully explain all of our observations of nature. Nevertheless, even the failings of a scientific model can be useful because they often point the way toward building a better model. So the Greeks created many models to help explain many aspects of nature, including the properties of matter and the principles of motion. But for our purposes here, the most important of the Greek models was their Earth-centered model of the universe. But before we turn to its details, it's worth briefly discussing how ancient Greek philosophy was passed to Europe, where it ultimately grew into the principles of modern science. So Greek philosophy really began to spread widely with the conquests of Alexander the Great. Uh, Alexander had a deep interest in science, probably because he was a student of Aristotle. Alexander founded the city of Alexandria in Egypt, and his successors founded the renowned Library of Alexandria. And though it is difficult to distinguish fact from legend and stories about the library, there is little doubt that it was once the world's preeminent research center, housing up to 500,000 books written on papyrus scrolls. Most were ultimately burned, their contents lost forever. But the relatively few books from the library that survive today were preserved primarily thanks to the rise of a new center of intellectual inquiry in Baghdad in present-day Iraq. As European civilization fell into the period of intellectual decline known as the Dark Ages, scholars of the new religion of Islam sought knowledge of mathematics and astronomy in hopes of better understanding the wisdom of Allah. During the 8th and 9th centuries AD, scholars working in the Muslim Empire translated and thereby saved many ancient Greek works. Around AD 800, the Islamic leader Al-Mamun established a house of wisdom in Baghdad with a mission that was very similar to the Library of Alexandria's. It was founded in this spirit of openness and tolerance, where the House of Wisdom employed Jews, Christians, and Muslims, all working together in scholarly pursuits. Using the translated Greek scientific manuscripts as building blocks, these scholars developed the mathematics of algebra and many new instruments and techniques for astronomical observations. The latter explains why so many official constellations and star names come from Arabic. So, for example, the names of many of the brightest stars all begin with Al. For example, Aldebaran, Algol, that means the in Arabic. The Islamic world of the Middle Ages was in frequent contact as well with Hindu scholars from India, who in turn brought ideas and discoveries from China. Hence, the intellectual center in Baghdad achieved a synthesis of the surviving work of the ancient Greeks and that of the Indians and the Chinese. The accumulated knowledge of the Baghdad scholars spread throughout the Byzantine Empire, which was left over from the former Roman Empire. And when the Byzantine capital of Constantinople, now known as Istanbul, fell to the Turks in 1453, many Eastern scholars headed west to Europe, carrying with them the knowledge that helped ignite the European Renaissance. And we'll pick up at the European Renaissance in just a hot moment. Then now let's explore the Greek geocentric model in detail. The geocentric model, named because it placed a spherical Earth at the center of the universe, developed over several centuries. There's not one singular person who really developed the geocentric model. And we generally trace the origin to this guy right here, Thales. We talked about him last week when we mentioned his legendary prediction of a solar eclipse. But Thales was the first person known to have addressed the question of what is the universe made of, without resorting to supernatural explanations. His own guess was that the universe fundamentally consists of water and that the Earth is a flat disk floating in an infinite ocean. That wasn't even really widely accepted in his own time, but he did the job of just asking the question, suggesting that the world is inherently understandable, and thereby inspired others to come up with better models for the structure of the universe. So a more sophisticated idea followed soon after, proposed by a student of Thales named Anaximander. Anaximander suggested that Earth floats in empty space surrounded by a sphere of stars and two separate rings along which the sun and moon travel. We therefore credit him with inventing the idea of the celestial sphere, which we talked about last week as well. Interestingly, Anaximander imagined Earth itself to be cylindrical rather than spherical. He probably chose this shape because he knew that Earth had to be curved in a north-south direction to explain the changes in constellations with latitude. And because constellations don't change with longitude, he saw no need for curvature in the east-west direction. We don't, although Anaximander thought the Earth was cylindrical, we don't actually know when Greeks started to think that the Earth was round. But we do know that it was taught as early as about 500 BC by the famous mathematician Pythagoras. He and his followers most likely adopted a spherical Earth for philosophical reasons. The Pythagoreans had a mystical interest in mathematical perfection, and they considered a sphere to be geometrically perfect. More than a century later, Aristotle cited observations of Earth's curved shadow on the moon during lunar eclipses as evidence for a spherical Earth. So the idea of heavenly perfection became even more deeply ingrained in Greek philosophy after Plato asserted that all heavenly objects move in perfect circles at constant speeds and therefore must reside on these huge spheres encircling the Earth. The Platonic belief in perfection really just influenced astronomy, kept astronomy where it was for the next 2,000 years. Of course, Greeks did compare his model with observations and found Plato's model problematic. We already talked about last week with the apparent retrograde motion of the planets. That clearly shows that the planets do not move at constant speeds around Earth. But an ingenious solution came from a colleague of Plato's named Eudoxus. We don't have a surviving picture of him. But he created a model in which the sun, the moon, and the planets each had their own spheres nested within several other spheres. So individually, the nested spheres themselves rotated in perfect circles. By carefully choosing the sizes, rotation axes, and rotation speeds for these invisible spheres, Eudoxus was able to make them work together in a way that reproduced many of the observed motions of the sun, moon, and the planets in the sky. Other Greeks then refined on that model by comparing its predictions to observations and essentially just adding more spheres to improve the argument. And this is how things stood when good old Aristotle arrived on the scene. So whether Eudoxus and his followers actually believed these spheres to be real is up for debate, but Aristotle definitely did. In Aristotle's model, all the spheres responsible for celestial motion, and you can see essentially what his universe looked like here. All those spheres were transparent and interconnected like the gears of a giant machine. They were actually like physical glass spheres in space on which the planets moved. Earth's position at the center was explained as a natural consequence of gravity. Aristotle argued that gravity pulled heavy things toward the center of the universe, thereby causing all the dirt, rock, and water to essentially collect at the center and form the Earth. Of course, now we know that Aristotle was not only wrong about gravity, he was wrong about his idea of the universe. But he was a very persuasive guy, and those arguments kept this being the working model of the universe for almost 2,000 years throughout the Western Hemisphere. It certainly didn't help that several hundred years after Aristotle, Greek modeling of the universe kind of got a rejuvenation with the work of Claudius Ptolemy. So Ptolemy's model still placed the Earth at the center of the universe, but it differed in significant ways from Eudoxus's and Aristotle's model. We generally refer to his model as the Ptolemaic model to distinguish it from earlier stuff. So to explain the apparent retrograde motion of the planets, the Ptolemaic model applied an idea first suggested by the Greek Apollonius nearly 2 centuries earlier. This idea held that each planet moved around the Earth on a small circle that turned upon a larger circle. The small circle is called the epicycle. The larger circle is called the deferent. A planet following this circle upon circle motion would trace a loop as seen from Earth, with the backward portion of the loop mimicking apparent retrograde motion. So here's an animation that I made. It took me several hours to make this animation. But the blue dot at the center is the Earth. The red dot to the right, we'll say it's Mars. It could be any planet. Mars is going to move along that smaller circle. It's going to move along the epicycle. But then that epicycle is going to move around the larger circle, the deferent. And as it does so, it will trace out an orbit. And every time it makes one of those little loops, in the sky, you would see that as apparent retrograde motion. And Mars's orbit is not exactly perfect, so it will those loops will shift over time. But this is, at the simplest case, essentially what Ptolemy's model did. Now, to match observations, it wasn't just one circle, one epicycle on the deferent, but it was many, many epicycles, circles upon circles upon circles to match observations. So that was his great accomplishment, that he was able to adapt and synthesize earlier ideas into a system that agreed well with the data that they were able to get at the time. In the end, his model could correctly forecast future planetary position to within a few degrees of arc, which is about the angular size of your hand held at arm's length against the sky. And this was accurate enough to keep this being the model of the universe for the next 1,500 years. When his book was translated by the Arabic scholars around 800 AD, they gave it the title Almagest, derived from words meaning the greatest work. So this was lauded across the Western hemisphere, not the Western hemisphere, across Western thought for many, many centuries. And the Greeks, among other things, they did develop many important scientific ideas, but what we now think of as science really arose during the European Renaissance. And within half a century after the fall of Constantinople, we begin our European side of it with none other than Polish scientist Nicholas Copernicus, because he began the work that ultimately overturned the Earth-centered Ptolemaic model. We call this whole period of time the Copernican revolution. And in many ways, it's the story of modern science, but it's also the story of many interesting personalities. And we'll start with none other than Copernicus himself. So Copernicus was born in Torun in Poland on February 19th, 1473, literally just a few, literally, I think like 20 years after Constantinople fell. So his family was wealthy, so he's able to be educated in many subjects, mathematics, medicine, law. He studied astronomy in his late teens. And by that time, tables of planetary motion based on the old Ptolemaic model have become noticeably inaccurate. But the calculations for producing tables of planetary positions were very difficult. The best tables have been produced some 2 centuries earlier under the guidance of the Spanish monarch, Alfonso X. He supposedly commented on the tedious nature of the work, saying, quote, "If I had been present at the creation, I would have recommended a simpler design for the universe." So in Copernicus's quest for a better way to predict planetary positions, he decided to try Aristarchus's sun-centered idea, first proposed more than 1,700 years earlier. He had read of Aristarchus's work and recognized the much simpler explanation evident for apparent retrograde motion offered by a sun-centered solar system. But he went far beyond Aristarchus in working out mathematical details of the model. Through this process, Copernicus discovered simple geometric relationships that allowed him to calculate each planet's orbital period around the sun and its relative distance from the sun in terms of the Earth-Sun distance. In other words, astronomical units. The model's success in providing a geometric layout for the solar system convinced him that the sun-centered idea was correct. Copernicus was, however, hesitant in his model. He feared that this would just be too absurd to consider that the Earth actually moves. But he discussed his idea with several other scholars, including theologians in the Catholic Church, and they urged him to publish a book. He saw the first printed copy of his book, De Revolutionibus Orbium Celestium, which is Latin for On the Revolutions of the Heavenly Spheres, on the day he died, May 24th, 1543. Publication of the book spread the sun-centered idea widely, and many scholars were drawn to its aesthetic advantages, but it didn't really get many converts over the next 50 years for a good reason, because it didn't really work that well. The primary problem was that while Copernicus was willing to overturn the whole Earth-centered idea, Copernicus still faltered and believed that orbits had to be perfect circles. And that incorrect assumption made him add numerous complexities to his system. In the end, his complete model was no more accurate and no less complex than the Ptolemaic model. So few people were willing to throw out thousands of years of tradition and precedent for a new model that worked just as poorly as the old one. And part of that difficulty faced by astronomers in picking between the Ptolemaic and the Copernican model was the fact that they didn't really have much quality data. The telescope hadn't even been invented yet, and existing naked eye observations weren't very accurate. So better data was definitely needed. And for that, we turn our attention to the Danish nobleman, Tycho Brahe. Tycho was an eccentric genius who once lost part of his nose in a sword fight with another student over who was the better mathematician. I'm very thankful that while I was in high school, that is not what math team meant. When I went to a math team competition, we didn't get out our scalibers. He did design a replacement nose made out of silver and gold. In 1563, Tycho decided to observe the widely anticipated alignment of Jupiter and Saturn. And to his surprise, the alignment occurred nearly 2 days after the Copernican model said it was going to happen. So he wanted to improve the state of astronomical prediction. And so he went out and did all those careful observations of the positions of planets and stars in the sky. His fame grew when he observed a nova in 1572. He measured its parallax and compared it to the parallax of the moon and proved that the nova was much farther away than the moon. In 1577, Tycho made similar observations of comets, proving that they were heavenly bodies and not phenomena of the Earth's atmosphere like Aristotle thought. King Frederick II of Denmark decided to sponsor Tycho's ongoing work, giving him money to build an unparalleled observatory for naked eye observations. And after Frederick II died in 1588, Tycho moved to Prague, where his work was supported by the German Emperor Rudolf II. And then over a period of 3 decades, Tycho and his assistant compiled naked eye observations accurate to within less than 1 arc minute, which is less than the thickness of a fingernail viewed at arm's length. Despite the quality of his observations, Tycho was never really able to come up with a model of his own for how the solar system worked. He was convinced that the planets must orbit the sun, but remember, the Earth isn't a planet yet. So he was convinced the planets orbited the sun, but then all of that orbited the Earth. This wasn't even taken seriously in his time, as it isn't in ours. So Tycho definitely failed to explain the motions of the planets, but he did succeed in finding someone who could. In 1600, he hired a young German astronomer named Johannes Kepler. Tycho and Kepler had a strained relationship, but Tycho definitely recognized the talent of his young apprentice. And in 1601, as Tycho lay on his deathbed, he begged Kepler to find a system that would make sense of his observations. So, quote, that it may not appear that I have lived in vain. Kepler himself was a deeply religious man, and he believed that understanding the geometry of the heavens would bring him closer to God. So like Copernicus, he believed that planetary orbits should be perfect circles. So he worked diligently to match circular motions to Tycho's data. And Kepler labored, in particular, on Mars. Mars disagreed the most with Tycho's observations. And he was able to get a circular orbit that matched Tycho's data along the ecliptic, along the east-west direction on the sky. However, the model did not accurately predict Mars's position north-south in the sky. And unlike Ptolemy and Copernicus, he could not tolerate one model for the east and west positions and a different model for the north-south positions. So in doing so, he found that some of his predictions differed from Tycho's observations by as much as 8 arc minutes. And I imagine that Kepler was definitely tempted to just chalk these discrepancies up to Tycho's faulty data, but Kepler trusted Tycho's work. He worked with the man. He knew the accuracy, the painstaking lengths Tycho went to get accurate data. So these small discrepancies finally led Kepler to abandon the idea of circular orbits and obviously to find the correct solution to this ancient riddle of planetary motion. About this event, Kepler wrote, quote, "If I had believed that we could ignore these 8 minutes of arc, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore, those 8 minutes pointed the road to a complete reformation in astronomy." So Kepler's key discovery was that the planetary orbits are not circles, but are in fact a special kind of oval called an ellipse. So you can draw a circle by putting a pencil on the end of a string, tacking the string to a board, and pulling the pencil around. You'll make a circle that way. Drawing an ellipse is similar, except that you must stretch the string around 2 tacks. So this animation, another animation I made, illustrates how you draw an ellipse. So the 2 points are the 2 tacks, and the nice sort of green line is the string. So as we pull the pencil around, it's going to draw out this white shape. And that white shape is what is known as an ellipse. So the location of these 2 tacks are called the foci, just talking about one of them, the focus of the ellipse. The long axis of the ellipse is the major axis here in red, each half of which is the semi-major axis in cyan. As we'll see shortly, the length of the semi-major axis is very important. The length of the short axis is called the minor axis in orange. And by altering the distance between the 2 foci while keeping the length of the string the same, you can draw ellipses of varying eccentricity. Eccentricity is a quantity that describes how much an ellipse is stretched out compared to a perfect circle. So you can see here, a circle has an eccentricity of 0. It's not stretched out at all. The 2 foci are essentially overlapping at the center of the circle. But as you keep the string, the circumference of the circle the same, but pull those 2 foci out from under each other, you'll stretch the circle essentially. And so if you stretch it a little bit, you'll get a moderately eccentric ellipse. Stretch it a lot, you'll get a highly eccentric ellipse. Stretch it too much, you'll break the ellipse and get a completely different shape altogether. So Kepler's decision to trust the data over his preconceived beliefs really marks an important transition point in the history of science. Once he abandoned perfect circles in favor of ellipses, Kepler soon came up with a model that could predict planetary positions with far greater accuracy than either Ptolemy's or Copernicus's models. Kepler's model withstood the test of time and became accepted not only as a model of nature, but also as a deep underlying truth of planetary motion. So Kepler summarized this discovery with 3 laws, which we now call Kepler's laws of planetary motion. So we'll go through each of the 3. So Kepler's first law says that the orbit of each planet about the sun is an ellipse with the sun at one focus. So this law tells us that a planet's distance from the sun varies during its orbit. Its closest point is called perihelion, which comes from the Greek words meaning near the sun, and its farthest point is called the aphelion, which means away from the sun. You can always remember which is which because away and aphelion both start with A. That's how I remember it in my head. The average of a planet's perihelion-aphelion distances is the length of its semi-major axis, which we'll simply refer to as the average distance from the sun. So here's an ellipse. You can see the sun is the yellow star. We've got a nice bright blue planet. You can see I've marked the perihelion, the aphelion, the semi-major axis, and then that small little open circle near the aphelion. There's nothing at that focus. It's just the sun at one of the foci. Kepler's second law states that a planet moves faster in the part of its orbit nearer the sun and slower when farther from the sun, sweeping out equal areas in equal times. So as shown in this animation I made, this one really took a while. To save this animation, I had to leave my computer running overnight, and even then it didn't fully save the animation. You'll see it jump in a second. So the sweeping in Kepler's second law refers to an imaginary line connecting the planet to the sun, and keeping the areas equal means that the planet moves a greater distance and hence is going faster when it is near perihelion than it does in the same amount of time near aphelion. So all these blue shaded areas on this ellipse are the same area. They take the same amount of time for the planet to move. But you see, when it's closer to the sun, it's able to sweep out more along that arc. It's moving faster. As when it's further away from the sun, it can only sweep out, to keep the area the same, it only can sweep out just a tinier bit. So it's moving slower at aphelion away from the sun. That's Kepler's second law. Finally, Kepler's third law says that more distant planets orbit the sun at slower average speeds, obeying the precise mathematical relationship p² = a³. So here, P stands for the orbital period in years, and A for its average distance from the sun in astronomical units. So these are two plots that I threw together. So on the left, on the vertical, we have the orbital period squared in years squared. On the horizontal, we have the semi-major axis cubed in astronomical units cubed. And I plotted the actual data for the naked eye planets, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, in white. Those are the white points. And the red line is that relationship, period squared equals distance cubed. And you can see the planets fall exactly on that line. So this is a very good observation by Kepler. Because Kepler's third law relates orbital distance to orbital time, we can use the law to calculate a planet's average orbital speed, which is what the plot on the right shows. So on the vertical, we have orbital speed in kilometers per second. On the vertical, we have orbital speed in kilometers per second. On the horizontal, we have semi-major axis and astronomical units. Once again, the white dots are Mercury, Venus, Earth, Mars, Jupiter, and Saturn. And the red is Kepler's prediction. And once again, it follows it extremely well. There is not a hard deviation from that line. So the fact that we now know that distant planets move more slowly led Kepler to suggest that planetary motion might be the result of a force from the sun. He even speculated about the nature of this force, guessing that it might be related to magnetism. Obviously, magnetism is not correct. Kepler was right about the existence of a force, but it took Isaac Newton to realize that's not magnetism, it's gravity. And we'll get to that next week. So the success in Kepler's laws in matching Tycho's data provided strong evidence in favor for Copernicus's placement of the sun at the center of the solar system. But nevertheless, many scientists still objected to it. We'll get to those objections in a moment. I keep getting ahead of myself in these. But first, here are some questions that, like I keep telling you, I want you to pause the video and think about an answer to before I reveal the answers. So when we say that a planet has a highly eccentric orbit, we mean that A, is spiraling in towards the sun, B, its orbit is an ellipse with the sun at one focus, or C, in some parts of its orbit, it is much closer to the sun than in other parts. Second question is, Earth is closer to the sun in January than in July. Therefore, in accord with Kepler's second law, A, Earth travels faster in its orbit around the sun in July than in January. B, Earth travels faster in its orbit around the sun in January than in July. Or C, it is summer in January and winter in July. And then finally, according to Kepler's third law, A, Mercury travels fastest in the part of its orbit in which it is closest to the sun. B, Jupiter orbits the sun at a faster speed than Saturn. Or C, all the planets have nearly circular orbits. So pause the video, think about some answers, and then unpause the video. I'll tell you what the answers are. All right, so I guess you've unpaused the video now. Let's go through the answer. So the answer to the first question is C. Eccentricity has nothing to do with a planet spiraling in towards the sun. And although B is technically correct, that doesn't really have anything to do with eccentricity. That's just Kepler's first law restated. The answer to the second question is B. Hopefully you knew that C was just flat out wrong. And A is incorrect. Since Earth is closer to the sun in January, then it's going to be moving faster in January, not in July. And then the final one, according to Kepler's third law, the correct answer is B. So A is correct, but that's Kepler's second law. C is correct. That's not a law. That's just a general observation. They are nearly circular orbits. So B is the correct answer. So note that I kind of quizzed you on all of Kepler's three laws. So if you didn't understand one, go back to this part of the video where I talked about that particular law. So now let's go back to those objections I was about to mention. So there were still scientists who voiced objections to the Copernican view, all rooted in those 2,000-year-old beliefs of Aristotle. So first, Aristotle held that Earth could not be moving because if it were, objects such as birds, falling stones, and clouds would be left behind as the Earth moves away. Second, the idea of non-circular orbits contradicted Aristotle's claim that the heavens, the realm of the sun, the moon, the planets, and the stars, must be perfect and unchanging. Third, no one had detected the stellar parallax that should occur if the Earth orbits the sun. And it came to our man Galileo to answer all three objections. So Galileo diffused the first objection with the experiments that almost single-handedly overturned the Aristotelian view of physics. In particular, he used experiments with rolling balls to demonstrate that a moving object remains in motion unless a force acts to stop it, which is now codified in Newton's first law of motion, which we'll talk about in depth more next week. So this insight explained why objects that share Earth's motion through space, such as those birds, clouds, and falling rocks, should stay with the Earth rather than falling behind, as Aristotle had argued. This same idea explains why, if you've ever taken a trip on an airplane, even though the airplane's moving, you can get up and move around and be perfectly fine. The second objection had already been kind of challenged by Tycho's observations of the supernova and comets, which proved that the heavens could change. But Galileo's telescopic observations, because he built a telescope in 1609, really were the final nail in the coffin on that objection. So through his telescope, Galileo saw sunspots on the sun, which were considered imperfections at the time. He also used his telescope to prove that the moon has mountains and valleys like the imperfect Earth by noticing the shadows cast along the dividing line between the light and dark portions of lunar face. These are his actual drawings, by the way. So the heavens were in fact not perfect, and the idea of elliptical orbits rather than the perfect circular ones were not so objectionable. The third objection, the absence of observable stellar parallax, was particularly concerning for Tycho, because based on Tycho's estimates of the distances of stars, he believed that his observations should be able to detect those the stellar parallax if the Earth did in fact orbit the sun. Sorry, excuse me. But although Galileo did not actually prove this fact, he did provide strong evidence in its favor. For example, he saw with his telescope that the Milky Way resolved into countless individual stars. That meant that those stars were far more numerous and way more distant than Tycho believed. Therefore, they were too distant to view with your unaided eye as stellar parallax. In hindsight, the final nails on the coffin of the Earth-centered model came with two of Galileo's earliest discoveries through the telescope. First, he observed 4 moons clearly orbiting Jupiter, not Earth. I put a little animation to show you what this might have looked like. However, it showed that the moon, this observation did not rule out a stationary Earth, but it showed that moons can orbit a moving planet like Jupiter, which overcame some critics' complaints that our moon could not stay with a moving Earth. Soon thereafter, he observed that Venus goes through phases in a way that makes sense only if it orbits the sun and not Earth. So now Earth is removed from its position in the universe. The scientific debate turned to how, if Kepler's laws were the correct model for our solar system. And that the most central piece of evidence came in 1631 when astronomers measured a transit of Mercury across the sun's face. So Kepler's laws had predicted the transit with overwhelmingly better success than any other model. And although we now recognize that Galileo sort of won the day, the story was obviously way more complex during his time, when Catholic Church doctrine still held the Earth to be the center of the universe. So on June 22nd, 1633, Galileo was brought before a church inquisition in Rome in order to recant his claim that the Earth orbits the sun. Nearly 70 years old and fearing for his life, Galileo did as ordered and his life was spared. However, legend has it that as he rose from his knees, he whispered under his breath, "Eppur si muove," which is Italian for, "and yet it moves." The church did not formally vindicate Galileo until 1992, but church officials gave up the argument long before that. So in 1757, all works backing the idea of a sun-centered solar system were removed from the church's index of banned books. Moreover, Catholic scientists have now long worked at the forefront of astronomical research, and today's official church teachings are compatible not only with Earth's planetary status, but also with theories of the Big Bang and the subsequent evolution of the cosmos and that of life itself. So now we've sort of covered the general history of astronomy up until we get to Newton. And I want to talk about now kind of the nature of science in general, because the story that we've told so far gives some great examples of what we consider good science. So we've seen how models were formulated and tested against observations and modified or replaced when they failed. But it also the story of astronomy also illustrates some classic mistakes. like the apparent failure of literally anyone before Kepler to question the belief that orbits have to be circles. The ultimate success of the Copernican revolution led scientists, philosophers, and theologians to reassess everyone's modes of thinking that played a role in the 2,000-year process of discovering Earth's place in the universe. So let's examine how the principles of modern science kind of emerged from these periods and from this period of the Copernican revolution. So it's hard to define the word science. Science comes from the Latin word scientia, which means knowledge, but obviously not all knowledge is science. So you probably know what music you like, but it's not like you put out a scientific study to figure out what kind of music you like. So one reason to why it's so difficult to define what science is because not all science works the same way. So for example, you probably heard that science is supposed to follow something called the scientific method, which is a nice illustration here. And we could visualize this if you think about what would happen if your flashlight suddenly stopped working. So you might hypothesize that the batteries might have died. This type of explanation is a hypothesis, which is sometimes called an educated guess, because you obviously have experience with flashlights going dead, and you know that flashlights need batteries. So your hypothesis allows you to make a simple prediction. So if you replace the batteries with new ones, the flashlight should work. If the flashlight now works, you've confirmed your hypothesis. If it doesn't, you must revise your hypothesis or reject it perhaps in favor of some other one, like the bulb might be burnt out. And although this is a useful idealization, and I apologize to any science teachers watching this, because this was a major problem I had when I was working on science fair projects in high school, that it was too rigid with creating a hypothesis, worrying about independent and dependent variables and rationales and whatnot. Most of the time, science is just someone going out and looking at nature in a general way, rather than progressing in an orderly way, conducting a careful set of experiments. So, for example, Galileo wasn't looking for anything in particular when he pointed his telescope at the sky and made his first discoveries. Furthermore, scientists are human beings. And their intuition and personal beliefs will invariably influence their work. Copernicus, for example, adopted the idea that Earth orbits the sun, not because he had tested that idea, but because he felt it made more sense than an Earth-centered universe. So while his intuition guided him toward the correct idea, he erred in the specifics because he still held Plato's ancient belief that orbits must be perfect circles. So given that this kind of scientific method idealization is way too generalized, is way too simplistic, how can we tell what is science and what is not, if not all science actually follows the scientific method? So one way to distinguish what scientific thinking is to list the criteria that scientists use when they judge competing models of nature. So historians and philosophers of science examine and continue to examine and debate this to great extent, and differ wildly, but everything we now consider to be science shares the following three basic characteristics, which we'll call the hallmarks of science. So modern science seeks explanations for observed phenomena that rely solely on natural causes. Science progresses through the creation and testing of models of nature that explain the observations as simply as possible. And a scientific model must make testable predictions about natural phenomena that will force us to revise or abandon the model if the predictions do not agree with observations. So each of these hallmarks is evident in the Copernican revolution. The first shows up in the way Tycho's careful measurements of planetary motion motivated Kepler to come up with a better explanation for those motions. The second is evident in the way several competing models were compared and tested, most notably that of Ptolemy, Copernicus, and Kepler. And we see the third in the fact that each of those models could make precise predictions about the future motions of the sun, moon, planets, and stars in our sky. Kepler's model gained acceptance because it worked, while the competing models lost favor because their predictions failed to match the observations. However, that criteria of simplicity in the second hallmark requires additional explanation. So remember that Copernicus, his original model did not match the data noticeably better than Ptolemy's model. If scientists had judged this model solely on the accuracy of its predictions, they might have rejected it immediately. But there were reasons that they kept Copernicus's model alive, such as its simple explanation for the apparent retrograde motion. If agreement with the data were a sole criterion, then we could imagine going back to Ptolemy's model and just continuing to add millions or billions of circles to match the data as the data got better and better. But even a sufficiently complex geocentric model would not convince us that the Earth is the center of the universe. We would still choose the Copernican model over the geocentric one because its predictions would be just as accurate, but follow a much simpler model of nature. This idea is called Occam's razor. He maybe not. There's a debate around what he actually said, but Occam said that entities must not be multiplied beyond necessity. In other words, scientists should prefer the simpler of two models if those models agree equally well with observation. This is called Occam's razor, named after William of Occam, a medieval scholar. That third hallmark of science forces us to face the question of what counts as an observation. Against which a prediction can be tested. So consider the claim that aliens are visiting Earth in UFOs. So proponents of this claim say that thousands of eyewitness reports of UFO encounters provide evidence that it is true. But do those reports count as scientific evidence? Excuse me. On the surface, the answer isn't obvious because all scientific studies involve eyewitness accounts on some level. So, for example, only a handful of scientists have actually personally made detailed tests of Einstein's theory of relativity. And it's their personal reports of the results that have convinced other scientists in the theory's validity. However, there's a difference between the personal testimony about a scientific test and a UFO. The first can be verified by anyone in principle, while the second cannot. Understanding this difference is crucial to understanding what counts as science and what does not. Even though you may have never conducted the test of Einstein's theory of relativity yourself, there's nothing stopping you from doing so. It might require several years of study before you have the necessary background to conduct the test. But you could then confirm the results reported by other scientists. In other words, while you may currently be trusting the eyewitness testimony of scientists, you always have the option of verifying the scientific testimony for yourself. In contrast, there's no way for you to actually verify someone's eyewitness account of a UFO. Without hard evidence like photographs or pieces of the UFO, there's nothing that you could evaluate for yourself, even in principle. Moreover, scientific studies of eyewitness testimony show it to be notoriously unreliable because different eyewitnesses often disagree on what they saw even immediately after an event has occurred. This is why in American criminal court, eyewitness testimony is insufficient for a conviction. You need some other sort of physical evidence to convict. For the same reason, we cannot accept eyewitness testimony by itself as evidence in science, no matter who reports it or how many people offer similar testimony. And no matter who reports it includes Neil deGrasse Tyson, includes Avi Loeb, includes every scientist you've ever heard of, including me. Everything I'm telling you in these public talks, you don't have to trust it. Admittedly, it's not all I'm not doing eyewitness testimony here, but you can go out and learn about this for yourself and verify that it makes sense to you. It is important to notice that science is not the only way of seeking knowledge. For example, if you're shopping for a car, learning to play drums, or pondering the meaning of life, you might make observations, exercise logic, and test hypotheses. But this is not science because they are not directed at developing testable explanations for observed natural phenomena. As long as non-scientific searches for knowledge make no claims about how the natural world works, they do not conflict with science. However, you will often hear claims about the natural world that seem to be based on observational evidence, but do not treat evidence in a truly scientific way. And we call that pseudoscience. So to distinguish real science from pseudoscience, a good first step is to check whether any particular claim exhibits all the hallmarks of science. So consider the claim that is repeated in news reports every year that on the spring equinox, you can balance an egg on its end. Oddly enough, there's a clip from the TV show West Wing that deals with this. So I'll play that for you.
At the exact moment of the equinox,
Doesn't work.
It does work. It has to be the exact moment of the equinox.
Doesn't work.
I've seen it.
I tried it.
And?
Doesn't work.
I don't think you did it at the exact moment.
I did.
When?
Last September.
That was the autumnal equinox.
It only works for the vernal equinox?
Yeah.
You know what's more likely?
That it doesn't work at all?
That's right.
It does. I've seen it.
We've got pastrami from Krupin's. It's tissue paper thin, roast beef, corned beef, turkey, Russian dressing, coleslaw, and seedless rye. And winning the hard-earned money of your coworkers. This is what I call a night off. Squeeze this piece of rye bread.
Now what do I do?
Excuse me, Leo.
Yeah.
Something that's true at the vernal equinox would have to also be true at the autumnal equinox.
Why?
Equinox means equal night. Night and day are both 12 hours long.
What does that have to do with it?
It doesn't work. I tried it.
Listen to the
Hang
guy.
on. CJ believes that at the exact moment of the vernal equinox,
And only at that moment.
you can stand an egg vertically.
Huh?
At the equinox, you can stand an egg on its end.
Yeah, that doesn't work.
You tried it?
No need to try it. You can't stand an egg on its end.
And the elements involved with creating an equinox have no connection to the center of gravity of an egg.
I've seen it.
Well, I've seen guys make the ace of spades jump out of their shoes. I don't think it was the equinox.
Josh?
So Toby, that guy at the end, was right. There is no connection between the point of time at which the sunlight strikes both hemispheres equally and the center of gravity of an egg. With enough practice, you can balance an egg on its end at any time of the year. And certainly if you were balancing the egg indoors, then the fact that there's an equinox and the sun's rays or whatever, it doesn't matter at all. So moving on from pseudoscience, I also want to talk about objectivity in science. So we generally do think of science as being objective, meaning that all people in principle should be able to find the same scientific results. However, there is a difference between the overall objectivity of science and the objectivity of individual scientists. Science is obviously practiced by human beings, and individual scientists bring their own personal biases and belief to their scientific work. So, for example, most scientists choose research projects based on personal interest rather than on some objective formula. In extreme cases, scientists have even been known to cheat, either deliberately or subconsciously, to obtain a result they desire. For example, in the late 19th century, astronomer Percival Lowell claimed to see a network of artificial canals and blurry telescopic images of Mars, leading him to conclude that there was a great Martian civilization. But obviously, no such canals exist, so Lowell must have allowed his beliefs about extraterrestrial life to influence the way he interpreted what he saw. In essence, a form of cheating, though almost certainly not intentional. Bias can sometimes show up even in the thinking of the scientific community as a whole. Some valid ideas may not be considered by any scientist because they fall too far outside the general patterns of thought or paradigm of the time. Einstein's theory of relativity provides an example. Many scientists in the decades before Einstein had gleaned hints of the theory, but did not investigate them, at least in part because they seemed too outlandish. The beauty of science is that it encourages continued testing by many people. So even if personal biases affect some results, tests by others should eventually uncover the mistakes. Similarly, if a new idea is correct but falls outside the accepted paradigm, sufficient testing and verification of the idea will eventually force a paradigm shift. In that sense, science ultimately provides a means of bringing people to agreement, at least on topics that can be subjected to scientific study. So I want to end tonight by just clarifying what is a scientific theory. So a scientific theory is a powerful yet simple model that makes predictions that survive repeated and varied testing. Some famous examples are Newton's theory of gravity, Charles Darwin's theory of evolution, and Albert Einstein's theory of relativity. But despite its success in explaining observed phenomena, a scientific theory can never be proved true beyond all doubt because future observations may disagree with its predictions. However, anything that qualifies as a scientific theory must be supported by a large, compelling body of evidence. So here, the theories of Newton and Einstein offer good examples. So a vast body of evidence supports Newton's theory of gravity, but in the late 19th century, scientists began to discover cases where its predictions did not perfectly match observations. These discrepancies were explained only when Einstein developed his general theory of relativity in the early 20th century. Still, the many successes of Newton's theory could not be ignored, and Einstein's theory would not have gained acceptance if it had not been able to explain these successes equally well. It did, and that's why we now view Einstein's theory as a broader theory of gravity than Newton's theory. Some scientists today are seeking a theory of gravity that will go beyond Einstein's. And if any new theory ever gains acceptance, it'll have to match all of the successes of Einstein's theory, as well as work in new realms where Einstein's theory does not. And that's kind of a general overview of the science of astronomy and how science works, as well as the history of astronomy. So that's one lecture down. Next week, we will put my physics degree to use, and we'll talk about motion, energy, and gravity before moving on to light and matter, ending off with telescopes, and then finally we'll start talking about astronomical observations in terms of the solar system. So thank you for watching this video. Definitely comment below what you enjoyed, if you're enjoying these videos, and definitely let me know if there's anything I can do to improve them. So thank you for watching.